I'm just going to talk about some of the recent work we have been doing here at Penn State. It's really about the integration with the devices on the human body for the diagnostic confirmation and potential treatment. So if we look at the start of electronics, it's really not something new, but back in 1930s, people have been thinking about these wearable, flexible devices. But if we are thinking about the target application on the fingertip and this really complicated geometry of the 3D topology, is now really something simple with the flexible geometry. Rather, we have to stretch them so that it can be easily deployed with the skin and also to accommodate the large deformation applied when we have the natural skin motion. So that's really why we are going after this stretchable deformation for the sensors. And in a general idea, we can use soft material, stretchable material, but rather here, to stick with the high performance devices, we use a structured design. Instead of using this large piece of electronics, we chop them into smaller pieces and use the interconnect to connect them. So it becomes stretchable. And this can be applied in this stretchable battery as well as the other potential application. I'm going to highlight a few more shortly. And for example, here is just to show we can capture all the information from the arm and to control the drone to fly wirelessly within the room without getting too deep. I'm going to skip the demonstration for the rest of the part, but just to show you the motion can be captured and control this fly within the room. And this can also be applied for the other sensors in terms of LED light emitting diodes for optogenetics application and for illumination. And can also be useful for hydration, strain sensor, temperature sensor, electro to capture the electrophysiological signal, but also to provide the treatment and feedback in terms of pain relief and also this closed loop feedback system. And this can also include wireless communication module. And now I'm just going to switch the gear and to move from the previous discussed photolithography-based approaches rather into a really rapid manufacturing approach. And just want to take one example as a stretchable gas sensor. They can be used for biomarker detection, industrial safety, environmental monitoring. And the idea is to use the highly sensitive gas molecule to be absorbed onto this gas sensitive detector. And this is typically nanomaterial. We can show that the morphology can be controlled, so it can be more sensitive to the gas molecule. And this can be wirely integrated onto a gas sensing platform. Typically, people would like to hook up the wire onto the single molecule. That would just be really the best in terms of sensitivity, but it's not possible due to the small dimension. And that's why literature will be using the interdigital electrode and then apply nanomaterial on top. So that's really a challenge to create a really small spacing between the fingers, and a lot of time and effort in terms of the cost will also be involved. So that's really the typical challenge number one. And second one is typically we need to have a separate heater to heat up the material. So the speed up process can be obtained in terms of detection and absorption of the gas molecule as well as the desorption, so that we can recover and then get that ready for next detection. So this tool can be actually eliminated with our novel gas sensing platform, so we can detect the gas molecule through this simple laser scraping process to create the highly porous structure from nano to micron nanometers. It can detect the gas molecule in actual high sensitive manner. It can be deformable onto the skin surface and capture the nitrogen dioxide for COPD, chronic pulmonary obstructive disease. And it can also be useful for the metabolic detection of different gases molecule. And this is why we're quite interested in this, because in the future, we're thinking to apply this on the human body to capture all the information and then transmit onto the smartphone or these other devices for the data analytics, and then information can be transmitted to a healthcare provider for in-time treatment. And of course, this highly porous structure is not only limited to gas sensor, but can also be applied for the other, say, pH, glucose, and a few others. And we can actually modulate the morphology from foam into fiber and to bump up the sensitivity much higher. And of course, this is not published, and we also don't have much time to get into that. But let me just skip the detail, but rather to talk about what we need to do in order to detect the glucose from the sweat. And the typical process is to do the blood sampling, but that will be really not really comfortable and easy to do for continuous monitoring, and it's also invasive. People would like to get around that issue if we can do the biofluids detection from the sweat, urine, interstitial fluid, saliva, tear. So that's why here we are going after sweat to collect the sweat from the sweat gland into the microfluid device and to control the flow and storage of this sweat. And the idea is to create this with a hydrophobic valve, and everything will be rendered to be hydrophilic, so the sweat can easily get into the channel without any problem. And when the sweat got collected in the chamber, it builds up the pressure and bursts open the valve, so you don't need to use a separate active valve or from the other complicated geometry design. So it's really simple. And we can do this collection through a really simple demonstration. You can see the sweat or liquid flow into the chamber and gradually fill in the entire chamber, and then it bursts open the valve and move on to the next one. So because of that, we can collect the sweat at different time points and also can do the measurement in terms of either electrical or colorimetric, so that you can directly see the color change indicating the pH variation. And this can be, of course, combined with a wireless transmission module, for example, antenna, that can be useful as a direct transmission component for the motion detection in the case here, but it can also be useful for stable operation of the wireless communication for the transmission of the data energy. So one way is to do this wideband. So if we have certain change, it doesn't matter that much in terms of, for example, wireless transmission of Bluetooth or Wi-Fi is centered around 2.4 gigahertz. So if you shift out of the band, it won't be something you can detect the signal, but rather if you have a wideband, they always cover the band, so it's not a problem. We can integrate this antenna with the other sensors in terms of electrode, hydration, pressure, temperature sensor, and microcontroller. All of this can be done within half an hour. So this is a really powerful approach to get this all done and integrated together. And from a different perspective, we can also integrate this with the narrowband but really robust so-called strain-insensitive antenna. It can allow us to transmit energy onto the antenna for harvesting and for analysis. And this can also be really robust. So in one demonstration, we have been transmitting energy from this 10 to 100 meters away, and the performance is robust in a way that is similar to what is in the freestanding case. So the body, the lossy tissue does not have a really big role. Actually, is negligible. So indicating we can actually integrate all this together. And separate node, we can do energy harvesting with a wideband antenna, so that can harvest energy from the ambient environment in terms of Bluetooth, Wi-Fi, microwave oven. So that will just be wasted if we don't harvest them. And theoretically, the limit is only about 0.1% in terms of efficiency to convert energy, because the dial is barely turned on at these low temperature, low energy levels. So what we have is really this wideband that integrates everything together. So to create the high efficiency, about 100 times higher, because you can see it's about like 10% also. So that's much higher than the theoretical limit of 0.1%. We can also design everything to be degradable if we select the biodegradable material, and the silk, PLG, the synthetic biopolymer can be selected as substrate. If we go to the drugstore, we can use the interconnects like magnesium, tungsten, zinc, and all of those are possible. And we are taking them every day, so that's why it's not a problem. And the electronic component are traditionally perceived to be stable, but actually they are dissolving. So when we put this together, we'll be able to construct the high fidelity and performance electronics over a large range of electronic components. And we can also program the time to dissolve from days to weeks, and that can be useful for a lot of different applications. To showcase one application, we have integrated, for example, inductor, capacitor, transistor, diode. So essentially every single component, so that you can combine them together for more sophisticated device demonstrations. So here is how the device dissolves in the water, and to showcase the degradable property. We can also apply this for the cerebral cortex mapping, brain monitoring in terms of temperature, intracranial pressure, and heart measurement of these different signals. And we can also create this all through the 3D integration, so that it's not limited to 2D, but rather to fabricate everything on the 3D beaker or even in the seashell. And this can create the new applications for smart Internet of Things to get everything connected. It can also enable, for example, a new modality for imaging. And this is the so-called electrical impedance tomography, which complements the existing approach for MRI, which is super slow in temporal resolution, but very good in the spatial resolution. So here we are trying to get that very fast to capture image, essentially at least a few thousand images per second, so we can clearly see how the chicken meat taken out of the petri dish, and then you can see all the information got displayed on the smart display, and then to visualize the information. And we can also deploy all the sensor on the human body to capture all the vital information for the infection. For example, COVID-19, to see how the patient go from mild into severe condition. So that's why we integrate multiple sensors and transmit the data through wireless communication. And this includes a few relevant sensors. So I know we are a bit over time due to the delay from the previous ones. So here I'm just going to get through all of those quickly, but rather to highlight the uniqueness of this approach. It first reduces roughness of this pore structure from paper, fabric, and we can easily fabricate the sensor. And this central A layer can reduce the central temperature from 600 degrees C down to maybe just room temperature if we select the nanoactive correctly. And the syntering will happen at the interface to enable less than 1 micrometer, so it's more robust against bending and deformation. And that's why when we compare this with approach published previously, is much better in terms of syntering temperature down to room temperature, and the conductivity is much higher over the others. When we try to bend and do different deformation, it's much better over the other approaches as well. And we can do the bending, folding, and crumping, and dipping in the water without any problem. We can provide origami paper structure for the electrical conduction and to provide the circuits as well. For the sensor, we can stamp them onto the surface and simply use a hair dryer to dry everything. So that will be easier to integrate on the skin surface. When we get to work with the COVID patient, we would like to know how the temperature varies, hydration, and blood oxygen change. So that's why we are moving to these different parameters to demonstrate they are as good and even better over the commercial devices, especially in this electrophysiological monitoring, for example, ECG and this heart rate monitoring. And the commercial device has a large impedance, and we can actually minimize that to be even more robust over the motion artifact. If you deform or do different exercise, and the sensor will still be robust to capture all this information. And this is really simply because the enhanced adhesion and more robust interface, and we can achieve high signal to noise ratio and better performance from this as well. Of course, people will wonder if we have a really enhanced adhesion, how can we take off? Because if we are working with elderly or the child, they have a delicate skin surface. So here we actually design this adhesive layer to be biodegradable. If you heat up the material over 50 degrees C also, you will be able to easily remove them. So if we take a shower or wash in the hot water flow, you will be able to remove them without any problem. So that's really the benefit of doing this all together into the integrated system. And looking into the future, we are working with a wireless self-power system. For example, in one example, we can integrate, for example, the stretchable micro supercapacitor for the powering of the device, like a strain sensor. And this can be charged up by a tribal electric energy harvester. So in one embodiment, we can put this on the clothing or on the human body. So say for moonlight practice in martial art, or when we're doing daily activities, we can capture all this vital information while providing the powerful device through these different activities. And we are also doing multimodality sensor integration to integrate piezoelectric and piezoresistive sensor, not only to detect the pressure and also the rate, but also the complex loading process. So if we're looking at this complex loading from the skin surface, we can reconstruct everything with a human robotic interaction and to enable the human machine interface for the future applications. So looking into the future, I think we'll have a lot of different opportunities for even biomarker detection for mRNAs and ultrasonic arrays, and even skin graft for the promote wound healing process. So without much time, I will just stop here. And of course, you have my contact information. If you have any other questions, feel free to reach out to me with emails or questions, and I'm happy to answer any questions if you have any at this moment. Thank you so much for your attention.